so let's get back to business. We are doing the weak field case. So the spin-orbit interaction forces us to use the label JMJ, but that is quite bad for the Zeeman term because the Zeeman term does not formally go parallel with J. We found a way out by projecting the extra S onto the J direction and take that component and we will be happy. Okay, so that is the idea. And so we do that, and then L plus S, that is J plus S, that is L plus 2S, becomes a factor and then J. This is approximated. We ignore the other components. There is a very good question. Xiaofan, he asked why we didn't use the first order, the degenerate perturbation theory. Okay, so I recast your question first. Why don't we use degenerate perturbation theory? Okay, so is that your question? Okay, so now first of all, we have in our toolbox this this degenerate perturbation theory. We can use it. Okay, so my first answer is that try to use it. Okay, Xiaofan, okay, try it. Okay, and then you will see that the result is just what we are going to get. Okay, so at least do you follow what I'm saying? Yes, okay, that is the fact first. And then you may wonder why, right? Now recall, in the degenerate perturbation theory, we take this subgroup of degenerate state and write down a matrix. Okay, do you follow me? Okay, it so happened, if we invoke this same approximation first, okay, that matrix is diagonal. Do you see? And that's why we can use this first order perturbation and get the same result. Okay, do you understand what I'm saying? Okay, so of course you are right. You are absolutely right. We have degenerate state. We should, because there are MJ hidden behind, right? So we should use degenerate perturbation theory. You are absolutely right. Okay, but the happy coincidence is that the same result comes out in a lazier way. Okay, get me? Very good question. All right, so now let me start here. Okay, after we project S onto the direction of J and ignore all the other components, we get really something that is parallel to J, but there's a prefactor. Okay, so now we apply first order perturbation theory. With this approximated to J, that's nice. Okay, as discussed before, the external field, then we will pick up JEZ. JEZ will look for this number and return MJH bar as eigenvalue. Thereby, we pick up the ball magneton as it should be. We are doing magnetic dipole moment interacting with a field. If you don't see ball magneton come out in your answer, there must be some problem. Okay, just like when you do electromagnetic problem, you don't see the charge coming out, there must be some problem, okay? So now we collect all this, okay? And it becomes mu b, external field, and the quantum number mj, all right? And now you see this factor, right? Because J squared will look for J, okay? L squared will look for L. S squared will look for this boring S times S plus half plus half plus half times half plus 1, okay? H bar squared, all right? So with all this, suddenly we have some pre-vector done, okay? So now this becomes a number depending on the quantum number in the state. But if you insert the number, it will no longer be a nice number. It may be 5.435, something like that, okay? So that combination, 1 plus something, 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 this whole chunk has a name. It is called the lambda G factor. It is defined as this. Remember, we introduced something called the term symbol last week. The term symbol, in one such symbol, include these 3 pieces of information. The L is in the middle, the letter, okay? 2s plus 1 is in the upper corner. J is in the lower corner. So when you see a term symbol, actually hidden behind is J, L, and S. You have all this, okay? And you can calculate it out, and then you get a lambda G factor. So let me summarize. Weak field case, spin orbit interaction required us to use this labeling. The spin orbit, the Zeeman term turns out to be slightly troublesome. We need to make one further approximation, more than just first order perturbation, but one further approximation of this extra term in the perturbation term, this S. We take the projection onto J, then everything goes very nicely. The price we pay is the G factor becomes a more complicated combination of the quantum numbers. Apart from that, the answer is very ordinary. When we apply an external field, it will split the degeneracy behind Mj. Remember, for a J, there are several Mj values. They are degenerate without the Zeeman external field effect. Now, J is 3/2. There will be 4 states. No field with field. Okay, even number. All right. So that is the effect, weak field Zeeman effect. I already explained this. Okay. So let's look at what happened. Let's look at again our favorite system, 2P. Okay, we did it for the strong field Zeeman. We find 5 different levels. Okay, now let's look at this. If we don't include any effect at all, not even spin orbit, there are 6 states. Fine structure, including spin orbit, we need to label by JMJ. And according to the J values, the energy will be different. So the degeneracy is not completely removed, only partially removed. The J can take on half and 3/2, which is 1 plus half and 1 minus half. Behind this, there are two states, Mj equals plus minus half. Behind this, there are 4 states, Mj from 3/2 to minus 3/2. So their degeneracy not removed. This is fine structure. JMJ label works. Now, with a weak field, we just found this will split into 4 states according to the MJ value. The spacing is given by lambda G factor times Bohr magneton times the strength of your magnet, the B field, okay? It's still equally spaced, but the G factor is something that you need to measure or you need to calculate, all right? And how about this J equals half state? They split, remove the MJ degeneracy again with a different lambda G factor, okay? And then mu BB, okay? Because the J value is different, okay? Do you see? That depends on J. So this spacing may not be the same as this spacing, all right? Nonetheless, we know what happened. The 6th state, 2p, now becomes, now this is highly exaggerated, I must say, okay? The actual splitting is, if this is the case, the 1s will be, I'm on the 2nd floor, okay? The 1s may be on the ground floor, okay? So, but just to make the point, the 6 states now really become, remove the degeneracy, okay? And fall into 2 classes according to the J value, and the MJ degeneracy is removed, okay? So that is the conclusion. So now we can understand why we have this funny, enormous Zeeman effect. Again, we look at our favorite hydrogen atom spectrum. This is the first Lyman line. Without anything, it is the line from 2p to 1s. You learn last term, this is minus 13.6 divided by 4. This is minus 13.6. So you can get this. This is the difference in EV, way out in ultraviolet. So you see one line. Okay, so that is 1880. Okay, something like when Barman, Lyman series, all those things were there. Now, with more quantum mechanics, we learn the following. Inside the atom, there is spin-orbit interaction. Even we don't have an external field, we have fine structure. That's what we discussed last week. We ought to relabel the state according to J, the 2p state, 3/2 and half. They are split by a little bit. We look at the number, okay? It is 1 wave number, 1 centimeter inverse out of 88,000 wave numbers, tiny. Again, it is out of proportion in this plot, just to make the point. Now it's split according to J, and with this spin-orbit interaction, we see what we call the fine structure in spectroscopy. This one line split into 2 lines, one here and here. Of course, the splitting is tiny, tiny, tiny. So here is this point, okay? And then there will be 1, 9 lower, 1, 9 higher, and the splitting will be 10 to the minus 4 eV, 1 over 10,000 of a eV, while this point itself is 10 eV. Okay, so on this scale, the 0 eV is way, 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 way out in New Asia College out there, okay, or even farther. Okay, so you must look at the scale. Okay, I'm exaggerating things and try to make the point. This is the fine structure. In sodium, you see that in your lab. That is the yellowish doublet in sodium lab. Okay, you use one of those in your lab work. What we did just a while ago is to apply a weak field. Okay, so now life becomes more interesting. Now we have J equals half here. There is Mj equals plus minus half. So that will give us 2 states. This will give us another 2. This will give us 4, okay? 4, 2, 2. 4, 2, and 2. Okay, so do you understand what is being done, at least for the horizontal lines? The 1s go into 2. 2 at 2p, j equals half, go into 2. J is 3 half, go into 4. Okay, follow me? I pause because the punchline follows. Okay? And later in the course, we will discuss what happens if we incident a light into an atom. That it has to do with not the atom alone, light atom interaction. That is something that we will discuss a little bit later. That has to do with time-dependent perturbation, another topic. But for the moment, I will just claim a result that the allowed transitions with light has to do with delta Mj is either 0 or plus minus 1. So that is called the selection rule for optical transition. Okay, the long sentence behind this is, these are the allowed transition relying on something called the electric dipole mechanism. It is not strictly the rule, because you can buy a very strong laser and induce some transition that is weaker, and then you can make it stronger by incident a strong laser field. All right, but this is at least the basic rule for the most important mechanism for light absorption and emission. Okay, so at this moment, I will just claim this selection rule, and then we can work out according to this rule, what are the allowed transitions. Take this upper 2p, mj equals 3 half. It is going to the 1s state. So there is a half and a minus half mj. Starting from 3 half, it can only go to half. It cannot go to 3 minus half because the delta mj will be too big. Light cannot supply such a deficiency of mj. Okay, that is some angular momentum here. Okay, so you only saw this line starting from 3 half. Okay, however, for mj equals plus half on this quartet, this 4 lines, it can come down to -half to the 1s as well as to the +half with delta mj being 0. That's allowed, okay? So you see why we have such many lines drawn. So you see 10 lines. Now that's the punchline. You see 10 lines, allowed transitions. And they are of slightly different energies. The energy difference, they are not the same. So previously, fine structure. Okay, come back here, you see 1 line. Higher energy means this line, okay? So in this figure, this is the dashed line, not here anymore. With a magnetic field, you will see around this fine structure line, 6 lines, okay? Now there is another one here. Previously here. In this figure is this dashed line. Now it becomes 4 lines. Okay? I must say it again. Even this spacing is 10 to the -4 eV. And here is even smaller. Okay? It is just a picture to make sure that you understand such splitting is rather complicated and there are 10 lines resulting. Okay? So, with the applied field conclusion, previously what we regarded as 1 line without anything, spin orbit Zeeman, becomes 10 lines. And that is the reason behind the enormous Zeeman effect. That also happens in sodium, because sodium happens that is a PP transition. I don't think that is a dominant one. If you trace the origin, okay, so there is a question why, asking why we don't have this gum to here, okay? A simple answer is that originally it's just here, there. So everything is hidden in this thing, okay? A deeper answer is that a P to P transition, you have the P state, which is something like a dumbbell, all right? You have another P, which is just like a dumbbell. You multiply them together, but now you are playing with light. Light, later on, we will see that we need to multiply a position operator in between. That is the electric dipole mechanism. That integral turns out to be 0. Okay, Mr. Choi? Okay, so in sodium, that happens in our visible range. So it's easier to see. Again, you see this doublet due to a fine structure further split into 4 plus 6. That is to say 10 lines. Okay, so that is the enormous Zeeman effect. Rather nice. We can explain it. Okay, not complicated physics, but good physics. Physics that we can handle. Only if you have a few tools in your hands, perturbation. Okay, so final remarks. We have start with Zeeman. Simple stuff. 1902 Nobel Prize, okay? Zeeman got that. But we realized that that is not sufficient because not only 3 lines, even number of lines. That took us through a long journey. We need to understand spin. We need to understand what is angular momentum generally in quantum mechanics, then we need to know how to add two angular momenta, okay? And then we investigate what is the form of spin-orbit interaction and why they are fine structure. And indeed, high precision spectroscopy saw that, okay? And then we go back and then add the field again. And today we discuss strong field limit and weak field limit. The strong field limit, strong Zeeman, weak spin orbit give us the ordinary so-called normal Zeeman effect again. But if the spin orbit is more important, the field is weak, we will see even number of spectral lines being split out, and then that has to do with dealing with the spin orbit part first, changing labeling to JMJ, and then the field split the degeneracy behind MJ. That could be even number of states. The transition will give us highly non-trivial Zeeman effects. Okay, and one final remark, we introduced the Landry factor by projecting the S in there, but I must mention that that was actually introduced prior to quantum mechanics, because spectroscopy has been a driving force of the development of quantum mechanics. You see, everything starts with the Balmer series, Lyman series. Okay, that is spectroscopy. 光谱学, 光谱学, okay. So when people use a magnet on a gas of atom, they start to see unusual things, and then they try to fit things to experiment. So this Landry factor was introduced earlier than quantum mechanics, just to describe experimental data. All right, and it has other applications, especially in magnetic atoms, or actually magnetic ions. But we don't have that many magnetic stuff in nature. Okay, look at the whole periodic table, maybe just a few of them. Okay, the most popular ones are manganese, iron, or cobalt, something like that, along the 3D, row in the periodic table. Okay, when we try to describe which one has a stronger magnetic property or weaker one, we usually look at the Landry factor. The bigger Landry factor indicates that this ion will be a better magnetic materials. Okay, so that's basically what I want to do for this part. Okay, so I still have 15 minutes, so let me start a bit about the next and final part of this part one of atomic physics module. So that will be the very last effect. That is an excellent question. What if the external and internal field are comparable magnitude? Okay, first, either we give up. Second, or don't try to make any approximation. Okay, we have the Hamiltonian, see whether you can solve it numerically. All right, you have the Hamiltonian, you try to find a reasonable basis, write it out as a big matrix, and then start diagonalizing it and see what happens. Okay, all right, that is the bad case. You have competing effect, but that is also usually some interesting things will come out. Okay, that is actually a theme in many different research topics in physics. You have similar strength of terms, okay? And then you have to do a lot more. Now, I would like to start discussing something called finer than fine structure. So it is called hyperfine structure. It means finer than fine, okay? Again, it means it is even smaller than fine structure. We have argued that fine structure is of order alpha square, okay? 1/137, but square. So it is already 10 to the minus 5, okay? Usually a 10 to the minus 5 EV order correction. But now we are going into a finer than fine structure, okay? What for, you may ask. Good question, okay? But it turns out that there are big consequences. For example, that will define what is a second. The SI unit of time. That will open up the whole area called radio astronomy. You have this big disk in Guizhou, okay? 500-meter aperture. And it is doing surveying the sky for what? For hydrogen atoms hyperfine structure. Okay, so let me start. Well, I think that is already good reason we look into it, okay? So, what we have up to this point without hyperfine structure, we have discussed n equals 2, we have 2s, 2p, but with fine structure, the splitting depends on n and j. So we have this 3/2, and we have two possibility of half, okay, come from s and p, okay? 0 plus half is half, 1 minus half is half. So that's why we have this, and they are of the same, these two are of the same energy, and this is the fine structure, okay? And then even the 1s will be shift because it depends on J, okay? So it shift down a little bit. This includes the spin orbit interaction and relativistic correction, or if we use the Dirac relativistic quantum mechanics equation, we will get this part. Okay, so we discussed this rather completely. But there is a part we couldn't explain further. But we look at the data. Data says there is still a little bit further splitting, and the n equals 2 will give us 3 states. Okay, highly exaggerated. This is one wave number out of, this will be 80,000, okay? And then there are some shifts that we cannot explain further due to QED effect. That is the Lamb shift. From data, we cannot explain it at this stage. That has to do with the vacuum, the space between the electron and the nucleus. We thought there's nothing, but nothing is a lot of things in quantum field theory, okay? So that is what we have. Now, we have a question in hand. The nucleus, that is the proton for hydrogen, is a spin-half particle. Therefore, it has charge plus E. It will have a spin angular momentum, and it will have a spin magnetic dipole moment. But this time, not for electron, but for proton. Okay? The question is, will that give some effect? Okay, so that is the question. We haven't taken into account of the proton spin yet. We have taken into account of the proton's Coulomb potential on the electron. We have done that. That's the Schrodinger part, YL and theta phi, everything, okay? But now we go back and ask, proton also spin half. Will there be an effect? Okay, so understand the question first. Okay, so at this moment, the proton, the nucleus has been given the following role. It supplies this into the Schrodinger equation. We did that. This U of R has a gradient, the electron moving in it, and the electron has a spin. This is electron spin. There will be a spin orbit interaction. So the proton has done something for us. This part and that part, pretty nice. But now it's time to ask a further question. Proton has spin half for itself and it is positive charged. So similar to an electron, opposite charge, there must be a spin magnetic dipole moment for proton. It has an effect. Okay, so let me advertise what the question is. We have been focusing on this electron, okay? We have been focusing on this electron. It has spin, all right? We study spin orbit interaction or everything, okay? This, so far, only provide the Coulomb potential, get me? But now we realize we ought to ask one further question. This is also spin half. The question becomes, two spin half particles, when we look at them together, that is to say, adding two spin half, what will we get? We will have spin, total spin equals 0, and total spin equals 1, right? Singlet, triplet state. Follow me? Huh? Pictorially, we can think about it like this. Singlet state is something like this, okay? One up, one down. But basically, we don't know which one is which, basically, okay? But one up, one down. Triplet state, they are more or less aligned. Remember how to add two spin half stuff, okay? So the question is, in the environment of a hydrogen atom, will this or that have different energies? Okay, the answer is yes. This has a slightly lower energy than that, and that is the hyperfine difference or hyperfine splitting. Okay, so do you understand the big picture? Okay, so that is the question, and that is the big picture. All right. Now with the big picture, things will be very easy. Okay, because we're not going to do detailed analysis. But there's one key concept that you must take in. Students for many generations, maybe high school education works too well here, always think in terms of what is the electron doing? What is one electron doing in an atom? They usually like to think the electron in 1s now make a transition to electron to 2p, okay? Now, that is okay if you have one particle only, the electron only. All right? But when you have helium atom, you have lithium atom, you have multi-electron atoms, you have 50 electrons, we better think the atom as one system, one quantum system. So here now, we have a two-particle system, two-spin system actually, nucleus plus electron. We better think of this as a whole atom system, okay? Not only thinking about what the electron is doing. Instead, we should think about this atom, okay? Many things inside, and then we ask, what are the allowed energies for this atom? Do you understand the question? I'm not thinking about whether the electron is somewhere at some level, okay? That for multi-electron atoms we will discuss next week, okay? That is a lot of approximation behind it until we can think about 2s, 1s2, 2s2, 2p4, something like that. Okay, that is already a very deep description, a lot of approximation behind it. An easier way to think about multi-particle system is just this whole thing as a system. What are the allowed energies? And you have the Schrodinger equation to solve for it, right? Okay. So here, I would like you to take in one idea. We are asking about now, we have a proton and an electron as one system. What are the allowed energies? Okay. So now let's do something very simple. Let's take in an experimental fact. The experimental fact is that proton alone is a charge plus E, spin half, okay? Therefore, it has its own spin angular momentum. A charged particle with spin is accompanied by a magnetic dipole moment. Now, this is subscript P, meaning proton magnetic dipole moment. It takes on the same quantum form, E over 2 mass. But now this mass is not electron mass anymore, but proton mass. It is proportional to the spin angular momentum without a minus sign because it is plus E. Okay? In electron, there's a minus sign. Okay? And now we have a G factor. For electron, this is 1. But for proton, experimental measurement tells us it's about 6. Okay, 5.6. Okay, it's about 6. Okay, so now we take it as an experimental fact. Proton is a tiny magnet. It has a magnetic dipole moment due to its own spin. Summarize. We can write the magnetic dipole moment of a proton as follows. Its own G factor, a new magneton, but not the Bohr magneton, but nuclear magneton. We call it subscript N, okay? It is the same expression, but 2,000 times smaller, okay? That means the effect will be tiny, that's hyperfine, okay? And now, it is proportional to this. And this is a number after dividing through H bar. This nuclear magneton is important because nowadays MRI is popularly used in research and in hospitals. And what we are talking about, hyperfine structure, things like that, are relevant actually to MRI. Okay, because MRI are probing the protons. We have many water molecules, H2O. So our body is full of H. You know, every water molecule has 2 hydrogen. So there are 2 protons, and this proton magnetic dipole moment is crucial for MRI's functioning. And look at this magnitude. It is 3 orders of magnitude smaller than the Bohr magneton. Okay, it's 10 to the minus 8 eV per Tesla. I will go through this page and then I will stop and then I will finish this whole part early Tuesday. Okay, so now what is the physical picture then? I have a magnetic dipole moment for proton. The electron out there also has a spin magnetic dipole moment of itself. We have 2 magnetic dipole moments. Look into your E and M, okay? So it's something like 2 magnetic dipole moments interacting. So how would they interact? They dot into itself, okay? That, and then the interaction energy will be, they dot into it themselves. It's mu A dot into mu B. You have A, B magnetic moments. So we expect some term like this into the energy term. And therefore, if we divide it by h bar, that will be a number and the energy will be in front. Okay? We don't care about what is it. We can look it up what it is. It's very tiny, 10 to the minus 6 eV, something like that. Okay? And now we know it is a dot product. So now the situation is as follows. We have, again, S1 dot S2. Both are spin half. Okay, so what to do? Define a total, right? Which is S1 plus S2. But we know how to add 2 spin half, right? So the quantum number will be 0 singlet or triplet 1. And we know how to handle this, right? You want a cross term, so you want square this thing, okay? Therefore, we expect this term will split according to S equals 1, higher energy, and then S equals 0, lower energy. This splitting is the hydrogen's hyper-fine splitting. The frequency is 1,420 megahertz. Change it to wavelength, it is 21 centimeter, about, okay? And for those who are fans of astronomy, you may have heard this 21 centimeter line of a hydrogen atom, and that is how astronomy has been surveying the sky. Look at the interstellar neutral hydrogen atoms, this particular transition. This is in the microwave region, therefore we have this radio telescope, many of them on Earth, okay? And then we can see, well, we now have this beautiful picture of spiral galaxies. Those are obtained by surveying this hydrogen 21 centimeter lines plus Doppler's effect. We know that trunk is moving away from us. That trunk is coming towards us. Therefore, we will have, I show you one picture and then I will stop. You will have such pictures, okay? And that is hyperfine structure of hydrogen 1s ground state, okay? So I will continue on and complete this part next time, and then we will start our discussion on other atoms. Helium, what to do? Lithium, what to do? Uranium, what to do, okay? So the whole periodic table. That will be a very difficult problem. Again, our philosophy is to find some ways out, making approximations as far as we can, okay? So that is a very interesting story. So I will stop here today. I will stay around. If you have questions, please ask. Bye-bye.